All right. Welcome back, everyone. This week we'll be talking about the chi-square distribution and the chi-square test of independence. Although, as the notes suggest and tell you, there are a few different uses that you can use the chi-square distribution for when it comes to testing hypotheses. The only one that you're expected to really know and master in this course is the chi-square test of independence, which we can also call the chi-square test of association. So before we can learn about, this chi-square test of independence, obviously we need to understand what do we mean by chi-square distribution. So that's where the notes start this week. And before I get into that, I'll just say at a high level, what we're interested in doing here is comparing mostly why we'll use the chi-square distribution as we'll talk about. It's mostly to look at the distribution, to compare the joint distribution of two categorical variables. And you might want to know whether these variables are related or are they not related? Are they associated? Are they not associated? Are they independent or are they not independent? For example, you might want to know whether, gender is related to pass fail for a certain class. So in this case, gender can be categorical. It is categorical, and pass or fail, you either passed or you didn't. That's also categorical. So there's two variables, and we could imagine we want to compare them and see is there an association between gender and passing grades. So that's the main question we'll answer. The main type of question we'll answer with the chi-square distribution. So let's start by learning what we mean by the chi-square distribution. So the chi-square distribution is like any other distribution. It belongs to this wider class of mathematics called probability distributions. And we've already learned a few different probability distributions. That is, we've learned the normal distribution, we've learned the z distribution, which is a normal distribution, but it's a very special type of normal distribution because it has a mean of 0 and a standard deviation and variance of 1. We also learned the t distribution. It looks a lot like a normal distribution, but technically it's actually not a normal distribution, although it is symmetrical and bell-shaped and all that. The reason it's not normal is because there's a little bit more variance, or we can also think of it as it has heavier tails than a normal distribution. So that is, more of the observations fall away from the middle where the mean is, and they feel closer to the ends of the tail. And one thing we learned about each probability distribution is they each have parameters. So parameters are these, we've talked about them repeatedly through the semester. Parameters are a theoretical concept, and they really tell us, if you know the parameters, exactly how you can draw these. You can draw any distribution if you know its if you know its parameters. So for the normal distribution, it has two parameters, the mean and standard deviation. The t distribution has one parameter, the df, and based on the df, like we studied in recent weeks, for a df of 1, it has larger tails. That is, more observations fall away from the middle. As the df goes up to 10, 20, 30, 100, infinity, it looks more and more like the normal distribution, and more of the observations fall closer to the center. So the chi-square distribution also has a single parameter, and it happens that this single parameter is called the degrees of freedom, just like our t distribution. And I think one of the better ways to study distributions, as I've done in the past, I like to see these things visually. So on the x-axis, we have a range of values. You could take 0, 5, 10, or 15 if you're in the case of the blue distribution. You see the green distribution has a little bit more variance. It goes from 0 to 25. And so you can see these are all chi-square curves, but just with a different df. And you'll notice they're definitely not normal, right? There's a lot of positive skew. That is right skew. The tail goes to the right. More observations of your data are falling farther away from the mean as compared to our normal distribution. And of course, because it's skewed, it's definitely not symmetrical. But you will notice as the df gets to 19, it actually starts kind of looking like a normal distribution. So as the df gets larger and larger, it actually does converge to the normal distribution. But as you'll see in the practice problems in these notes and also in the homework, typically we're in a low df situation. which means the chi-square distribution does not really look normal when we use it for hypothesis tests most of the time. So that's a little bit about the shape of the chi-square distribution. And we use the Greek letter chi and squared. And the reason why we call it the chi-square distribution, it's actually a distribution of squared terms. Like if you think of the variance, the variance we often have written as, say, sigma squared. It actually has a chi-square distribution. So the way I think of it is the chi-square distribution is really a distribution that's going to be quite common when you have any type of statistic which is squared. You'll see this thing coming into play, and we'll see that little rule of thumb I gave you. We'll see that in play in these notes later on. Okay. So I provided a lot of narration about learning about the chi-square. And as you're probably getting used to, every time we introduce a new statistical test, we have to talk about the distribution of the underlying statistics. That is the observed and the critical statistics. Those are the two things we need, right, to conduct any hypothesis test. And so the chi-square test we'll be learning this week. The reason why we're studying the chi-square distribution is it just happens because some statisticians have proved it in the past through mathematics. We've also proved it through simulation that variables or test statistics and critical statistics, they follow a chi-square distribution. And so we're going to use the chi-square distribution to start talking about, hypothesis testing, which means we're really going into the world of p-values and also critical statistics for creating rejection regions. Now, I didn't say it, but all probability distributions, the area under the curves sum to 1. And that's what allows us to make probability calculations here. And, remember, if we don't have a rule, if we're trying to compare two variables, like we're going to see in a little bit, we need to use these probability rules to give us, I'm going to put objective in quotes, but objective rules of thumb for when something is statistically associated and when it is not. And again, we'll look at this in a little bit because these procedures are not as objective as people would like to think they are. There are some, some things that are, I want to say things like sample size, things that are not really, you would hope would influence statistical significance, but they do influence statistical significance. But I will say kind of understanding the limitations and weaknesses of p-values, it's a concept that I want to speak to a little bit, but really that's beyond the scope of our course. And as you continue studying quantitative methods, you'll come back to criticisms and limitations of the p-value approach. In this class, it'll be, we mostly focus on learning the p-value approach and how to apply it. But I do want you to note there are some weaknesses with the p-value approach, which, because they are a bit more technical, we don't address head on. So just be aware of that, p-values are not always reliable in every single circumstance. In particular, if the assumptions of the hypothesis test you're doing are broken, the p-values are completely untrustworthy. So everyone agrees on that, and we'll talk about the assumptions required to conduct our chi-square test in a little bit. So our test and observed statistics follow chi-square distributions. And so we can denote, when we're talking about the critical statistic, we always have to go to the alpha level of significance. Remember, 0.05 is the conventional alpha that we use. And so we can write it, the chi-square statistic with alpha of 0.05. That's how we can write it. And, when we conduct our hypotheses test, remember the step 1 is we say the null and alternative. Step 2 is we talk about alpha and we go and get the critical statistic. So that's what we're talking about here, step 2. Alpha is always given, so I hope you're feeling comfortable with just, reading the instructions and following the alpha listed in the problem. If it's not stated, you always default to 0.05. This is true in this class, and also in practice, you just typically always default to 0.05 significance level. Now, there's one more piece of information we need to use before we can look up a critical value in a chi-square table. So the chi-square distribution, as we've talked about, it has one parameter called the degrees of freedom. So just like we needed the degrees of freedom when we looked up the critical value of a t statistic, we also needed the alpha value to look up t or z statistics. We're going to need both the degrees of freedom and the alpha here to use a chi-square table, just like we need both of them to use a t statistic. So this is a snapshot of the table which I've posted on Canvas, and I've given us a little fictional problem here. But let's suppose that you have a DF of 9, and we're using an alpha of 0.05. That's all the information I need to find my critical statistic. And you can see here, I've pointed the arrow to the alpha of 0.05. I've also put an arrow on 9DF, and then I just intersect them, and I get 16.919. So what that's saying then, let me draw this in a picture. What that's saying is that if my chi-square distribution looks like this, well, let me draw that a little nicer. It's saying this is 0.05, and it's saying that 16.9, that's the number here that leaves 5% area in the tail. Now, that area is the alpha level of significance. It's the type 1 error rate. That is, it's the probability of making a mistake if the null hypothesis is true. It's the probability of rejecting a null hypothesis when in fact it's true. So that's how we tune all alphas critical regions, is we're basically tuning the type 1 error rate. So just to give you a little refresher and reminder on that. And you can see I put a picture here. Now ours is 16.9, but you know, as your DF change and your area alpha level changes, you're going to have different critical statistics that are going to create different rejection regions, right? Now, I want to note one thing that's going to be different here from the weeks past. We do not have two-sided tails here. There's only one tailed test here. You're always going to be looking at it, area and the right. So, you know, maybe that makes it a little bit easier, but there are no two-tailed tests that you can do. And you'll see when we get to the Nolan hypothesis, it's because there's not really directionality. The nulls are literally, the factors are independent. And the alternative is the factors are dependent, which means they're correlated or associated. So there's not really two directions to think about this on. When we did, like, for example, comparing means, like if you had the treatment minus the control group, that could be a really big positive difference, or it could be a really big negative difference, right? There's directionality there. Here, there's not directionality. You're either independent or you're dependent. You're either associated or you're not, right? So we'll be in the one-tailed test land here as we learn our chi-square methods. Now, that's a little bit about the chi-square distribution. Let's talk about applications of the chi-square. And there's really three main applications that you're going to see. And this first one here is test about the value of the variance. This is really not that useful. In fact, honestly, I don't know if I've ever done this out of a textbook in my 10 years of being a statistician. So what I would say is, one you should be aware of, but you're probably not going to use it. And how I would think about this one. You remember when we studied the t-test, we studied the one sample t-test where we looked at whether mu1 is equal to some constant, say 15. We also had directional, like it could be greater than 15, right? So this is basically a test of the population mean, but you could imagine we might also be interested in test of the variance. Could it equal to 15? Versus the alternative, it is not 15, right? That is a plausible hypothesis test you may be interested in one day. And really the logic follows the same way. It's just the difference is, instead of a z distribution, the test statistic based on the variance parameter follows a chi-square distribution. So that's use case number one, a use case which you are not expected to know or master. Similarly, you're not expected to know use case two, but you will see use case two a lot more. As you advance your studies in quantitative methodology, you'll get to some types of modeling which use chi-square tests, which we call goodness of fit test. And this basically will tell you how well does the model fit the data. And for example, structural equation modeling, SEM, that's an advanced type of analytical modeling. They use chi-square goodness of fit test. But this is beyond the scope of our class. You'll see this in the future if you continue studying statistics. The third case is really what interests us today. That is the chi-square test of independence, or we can call it the chi-square test of association, right? If they're independent, they are not associated. Also, if they're associated, they're definitely not independent, right? So those are just independence, association. They mean they're opposites, right? So I've seen it referred to both names quite a bit. I couldn't tell you which is more common than the other. I think our book uses the chi-square test of independence, if I'm not mistaken. But when you're looking online and you know, materials online, you'll see many people calling it by this. So it's important to know there are two names here. And our example here is, let's say we have two categorical random variables, such as the amount of smoking, where you could be high, medium, low, or no, you don't smoke. You could also have age group, 20s, 30s, 40s, 50s, 60s. So you'll notice there's two factors, age and smoking. They're both categorical. And what we want to test is whether they're related or correlated, or are they not? So you can imagine this is an extremely useful thing to know about and to use in practice. Now, before we can introduce that test and its logic, we need to talk about contingency tables. So these are very useful descriptive statistic techniques. And in the first few weeks, we learned about frequency tables. So say I had a variable like eye color, which has, in this sample of data, blue, brown, green, and hazel. I could create a frequency table, which actually happens to be here in the right margin of the table. 215 people with blue, 220 brown, 64 green, 93 hazel, total 592. So this is actually this column with this column, that's a frequency table. You also have a frequency table of hair color here with there are 108 people with black hair, 127 blondes, etc. So in the margins of this table, outside of the bolded part, you actually have frequency tables. And these are, again, they're univariate frequency tables. Before the midterm, our focus was mainly on, if not entirely on, univariate statistics. That is how to present and interpret and report univariate statistics. And for categorical variables, there is no better way than showing a frequency table. Now, a contingency table or a two-way frequency table, it's not a univariate construct, it's a bivariate construct. It's showing what we call in probability theory the joint distribution of two factors. And so inside the bolded lines, that's actually our contingency table. The stuff outside of the bolding lines is helpful details, but when we refer to contingency tables in statistics, we're really just talking about the intersection of two nominal or ordinal, that is, two categorical factors. So I've written the notes with the intent that you would read them. So, you know, I'm giving you a voiceover here and doing a verbal presentation of it, but please read the notes and go slowly. I do find that contingency tables are pretty intuitive. So if you read the notes and really just look at it for a few minutes, I think you'll get it. But, you know, there are 7 people who are brown and blonde haired. There are 119 people who are both brown haired and brown eyed, etc. Right? Those frequencies are intersections of two different categorical variables. If you're comparing two categorical variables, there is no better way to visualize how they might be associated, or that is, there's no better way to visualize how your data is falling. And they may be associated or they may not be associated, but this is the first step we will take. before we can answer whether they're associated or not associated, I always come and look at my contingency table, and then I'll try to take a best guess on whether the chi-square test will be statistically significant or not. So again, please read the notes. They're really meant to be read in kind of a narrative format. So I want to give some examples here. I want to look at a fictional example, which I've made up, with a 2x2 contingency table. 2x2 because there's 2 columns, 2 rows. And that's the case because there's 2 categories of the smoke variable and 2 categories of the gender variable in this sample. And so all in all, you have 4 cells, right? And we call each little box here is its own little cell. Like if you've used Excel a lot and you're very familiar with that, you know that in Excel, it uses the same language, cell, to describe like a particular box and the data inside that box. Now, you'll notice that I have counts here in my contingency table. So there are 90 males who do not smoke. There are 10 males who do smoke. But you'll see I've also put percentages. And you can put column percentages. And I always, by the way, recommend that you do percentages like this somehow. So you can tell here, it's really helpful because I can see that 90% of males smoke, 91% of women, 90% of men do not smoke, and 91% of women do not smoke. So I would say that's pretty comparable, right? Doesn't really seem too different. If I were to resample 100 males and 100 females, I would expect to get about the same thing. And because of that, if I conduct a chi-squared test on this data, I wouldn't expect it to be statistically significant, right? The proportions between males and females who smoke aren't that different, 9 and 10%. So again, the column percentages are really going to help you interpret this data. They're actually what we call conditional probabilities. So conditional on being a male, you are 90% non-smoker and 10% smoker. So we actually call these conditional probabilities, which the book talks about. Of course, you can also show row percentages. I'll say column percentages are slightly more common, but you can show row if that's what makes sense in your data. And in this case, I've conditioned on smoking. So if you're a non-smoker, 50% of those non-smokers are males and 50% are women. We're rounding here, right? If you are a smoker, 53% were male and 47% were female. And you may be saying, well, hey, that's a bigger difference than I saw in that table. And that's exactly right. It's very misleading because it has a small head count. The percentages can be seeming more different than they really are. So you can see that people can deceive you with small sample sizes because this 6% difference among smokers, males are 6% more likely to be represented in that category. But that's very misleading because, 6% when you only have 19 head count is like, you can literally see it's 1 person difference. So up here where you have 181, you can see the rounding is still at 50%. So again, the reason why it looks misleading is because of the small head count, because you're conditioning on being a smoker and there's only 19 smokers. So that small little 1 person difference blows up to a 6%. So there's a book written by this guy named Duff, How to Lie with Statistics, and small head count making rates look very different is a one approach you will see people try to use to be dishonest. But we don't want to be dishonest, and that's exactly why we have this chi-square test of independence. It doesn't matter about your column or row percentages, and look, there's even a third option. You can just show the overall percentages, and here, 45% are males who do not smoke, 45% are women who do not smoke, 5% are men who smoke, 5% are women who smoke. There just doesn't seem to be a difference there, and your chi-square test would most likely confirm, hey, gender is not statistically associated with smoking. I will show you how to conduct the chi-square test in a moment. But before I do, I want to go to an extreme example where there's a clear, let's see, what was this one doing before? Where there's clearly an association between the 2 variables. So this one is showing no association. It's actually the same table from above. It's this table that's showing association because look, if you're male, you're a 90% non-smoker, in this fictional data, however, if you're a woman, you're a 90% smoker. Clearly, gender in this fictional data is a huge driver of the decision to smoke, and it's showing that women are much, much more likely to smoke than men. If we conduct a chi-square test on that, I would suspect that test would say the two factors are correlated, right? They definitely are not independent. So before you conduct chi-square tests, I always like to do that in my mind, kind of look at the data and make a prediction on whether I think it'll be statistically significant. Of course, in real data, it's not going to be huge separations like that, right? And I've actually got some real data here at the end of the notes here, which I'll go over. But looky here, this is a more realistic case of data you might see. So here we have 161 people. They're cross-classified on gender and whether or not they smoke. And so you can see if I'm looking at the males, it looks like about 40% are yes to smokers. For women, it actually looks closer to 50% are smokers. Okay, you know, proportions are maybe a little bit higher of women, but do I have enough evidence where that difference in proportion is statistically significant? It's subjective, right? You could ask different people and they might say, hey, yeah, I think that's meaningful. Some people might say, well, it's actually pretty close. We're talking about a few. So to remove that subjectivity, we introduce the chi-square test of independence. And like we do with all statistical tests, the first thing we do, we'll talk about what the null and alternative are. So the null is the two variables are independent, and we're going to compare that to the alternative. Hey, they're actually associated, right? So that's step one of every hypothesis test you'll ever do. You must list the null and the alternative, or you don't know what you're testing. And now we do have to digress a little bit and talk a little bit about mathematical theory before we can finish out, you know, our mapping out how we do the chi-square test of independence. And what we're going to do is, look, when you actually conduct a p-value, you're actually assuming the null hypothesis is true. And so that's what we're going to do here. Just like we've always done, we're going to assume the null is true. And if it was true, that is, if gender and smoking were independent, then given a sample size of 161, and if we know how many women and how many men there are and how many smokers and non-smokers there are, well, if they're independent, we can actually compute the expected cell frequencies. And these, remember, these expectations are assuming independence. So, you know, what we're basically going to do is if the data in my sample, these are the observed frequencies. If the observed frequencies are very different from the expected frequencies under independence, then we will reject the null and say, hey, it doesn't really look like the data came from a process which would suggest independence. It looks like there's actually a correlation between the two factors. And so that's what the chi-square allows us to do. It allows us to say how much do the observed and expected cell frequencies need to be different before we will label that difference as statistically significant. And so again, the notes are meant to be read. So go very slowly here. I know sometimes notation can be a little bit daunting when you first get exposed to it. So I have EIJ equals RICJ divided by N. So this is not as complex as it looks. What you're computing are the expected cell frequencies. So I refers to the row. So this is row 1. So notice how the first the first index is an I is 1 in both because it's the first row. Row 2 is down here, and notice how the first index is 2 because you're in the second row. And then column 1 is going to be the J or the second number here. So you got a 1 there, a 1 there, and then you got column 2 over here. So we need to understand that there are 2 subscripts here because they're mapping onto the rows and columns of our contingency table. That contingency table doesn't have to be 2 by 2. I'm pretty sure Here we have a 3x2 contingency table, right? So, okay, we have this formula, EIJ. I'm starting to get comfortable with what EIJ is, recognizing it, just talking about the different expected frequencies in our contingency table. Now, Ri is going to be the row total frequency. So as I look up here, the row total frequencies are going to be 65 for row 1 and 96 for row 2. So if you look here, remember we'll put the row first. That's convention. We will always usually put the row first. So look in the first row, 65, 65. R1, R1. Comes from right here. We have 96 for R2. Notice when we have R2, we're plugging in 96. So you see we're just plugging and chugging. Ends are always going to be 161 because it's the same sample size. So denominator will always be that. And then C1 and C2 are going to be the column frequencies, 106 for C1 and 55 for C2. So wherever you see C01, C1, you're going to be C106. C2 is going to be 55. So you plug those in and you get 4 expected cell frequencies. And so that's the first step. So what we're talking about is the steps you have to go through to calculate your observed test statistic. The first step is getting the expected cell frequencies, which are going to be calculated here, where we are assuming the null is true, that they're independent. That's basically what we're doing. Now, okay, that's the first step in calculating the observed test statistic. And you can see here the observed test statistic, as we've been doing, it's a chi-square, and I put a little obs for observed. So hopefully the notation and keeping clear what is a critical and an observed statistic, it's going to be just as important in this week as it was in the past. And you can usually look at the subscripts. Is there a little alpha there? It's going to be a critical test statistic. If it's an observed statistic. And we can see that the formula here is I got to sum over all the cells. So I've got 4 cells here. I'm going to take the observed minus the expected. I square it and then divide it by the expected again. So in my example, the observed frequencies 40, 25, 66, and 30. 40, 66, 25, and 30. They're the original data. That is the data you actually got. The expected, we had to calculate. And we actually calculated these above. And you can see, you know, ultimately they correspond. So I put it as a 2x2 table here. Here I've put it as 4 different rows because there's 4 different cells in our contingency table. And now I need to start applying this formula. So the first thing I have to do is O minus E. So observed minus expected. So look, 40 minus 42.8, 25 minus 22.2, etc. Then I need to square it. Then I need to divide it by E. By the way, it's just complete like luck that they all are 2.8. You're usually not going to get the same values every single time. That's just kind of crazy that actually happens in this problem. And then we're going to divide by E. So, you know, 7.84 divided by 42.8. 7.84 divided by 22, etc. is going to give you this value here. Let me circle it. This value, we got 4 of those, is this column. The sum we are applying down here. We're going to add them all up. So remember, that's what the capital sigma means. 100 times out of 100 in mathematics, you're summing the stuff on the right. And so in that way, we actually develop, this is the observed chi-square statistic. So there is a little bit of computation here. I'll say, you know, the 2 steps do take a little bit of time, but they're not that bad after you've done a few practice problems. Step 1 being calculate the expected cell frequencies. I really like to use Excel and lay my data out just like this. And I encourage you to do the same. Now, okay, That's how we get our observed test statistic. And again, we do need to find our critical test statistic. So in this case, the DF, as it says here, it says it in various places. It's the number of rows minus 1 times the number of columns minus 1. We have 2 rows and 2 columns. So because 2 minus 1 is 1, we actually get 1 times 1, which is 1. So in our case, the DF is 1. So I'm going to come to a chi-square table. So let me do this here. This is posted in Canvas under your general support resources. So I have a DF of 1 and I have a alpha, I believe, of 0.05. So 3.841, right? DF is in this column. I'm in the first row where DF is 1, and I'm in a 0.05 critical value, 3.841. Where are the notes? Here they are. So let's see. It looks like I did not. Oh, there it is, 3.84. And so in this case, if I were to draw a picture, let me draw this a little bit better. Our chi-square statistic is 0.899. The rejection region starts at 3.84. So that number is 3.8. You can see our test statistic is not in the rejection region. So we do not reject the null hypothesis. And we're saying that the data appears as though the 2 factors are independent. That is, they are not correlated or associated. So that is our chi-square test of independence or chi-square test of association. There's a second example, and I would leave that to you to do on your own. But again, all the math is here. And you'll notice this is a 3x2 example. So when you actually get to the DF, it turns out to be 2 because there are 3 columns. So you do 3 minus 1, which is 2. But it's the same dance. You got to compute the expected and then create this little table. And then remember that table, it's applying this formula. That's what we're trying to do there. Okay. So now I'm going to be very brief here on the assumptions. So the first thing, which I hope is clear, everything I've said in the last half hour or so, we're comparing 2 categorical variables. If I have 2 numeric variables, this is not the procedure for us. What kind of test do I use if I'm comparing 2 numeric variables? We will use the correlation test, which we're going to be learning next week. If you have 1 categorical variable that's binary, and you have 1 numeric variable, what test should you be using? You'll be using the t-test. And there's 2 different types of t-tests, as we saw. There's one for dependent samples and one for independent samples. But in both, you're comparing a categorical variable. It's got a 1 or 0, yes or no. There's 2 categories. We're taking the mean of those two categories on a different variable. So we might compare, say, gender to test scores. 2 and 3 are similar assumptions. You must have expected cell frequencies that are 1 or greater. And at most, 20% of the expected frequencies are less than 5. So you'll see this test in SPSS in a little bit. I'm going to show you how to do this in SPSS. Our expected frequencies are greater than 5, so that assumption is verified. So it's really that easy. You're just going to be basically comparing that. Observations are independent, so that means your data is independent, which means someone's score, say you're measuring heights, their height should not influence the height of someone else. So like if they manipulate the scale and make it biased, someone does that, well, it's going to create correlation in the bias. And so that would be like a violation. But of course, that's a very rare thing. Independence is usually safe to assume. And if it's not, then you use other types of procedures which account for that independence. Now, I want to talk about the odds ratio. It's an effect size for categorical data. So remember when we studied t-test, we talked about how the t-test is just a significance test. It will tell you whether a numeric variable is related to a binary categorical variable. It will tell you whether there is a statistically significant relationship. That's very helpful. But as I said earlier in this lecture, there are limitations to p-values. And the most obvious, although there are a few limitations, I like to just stick with head count. If I run a t-test and have 10 people in my sample, it doesn't matter how big the mean difference is, it will just almost never be statistically significant. On the other hand, if I have 1 million people in my t-test, even the smallest differences turn out to be statistically significant. So this is one of the issues with p-values, is in that they are functions of your sample size. But one way to get around that is to complement our p-values with an effect size. So just like we learned Cohen's d is a good complement to a t-test, this week we're going to learn that the odds ratio is a good complement to the chi-square test. And so where chi-square and t-test are significance tests, Cohen's d and odds ratios, I like to think of them, as Cohen said, they are about practical significance or clinical significance if you're in medicine or psychology. And so these effect sizes, they measure only the magnitude of association between two variables. And it turns out these effect sizes are independent of sample size, which is a pretty important property to have. So let's go ahead and learn our odds ratios effect size. Now, the good news is it's very easy to compute the odds ratio. So I'm going to do an example here. So this is actually from, I posted a dissertation on Canvas 2 weeks ago under the t-test section. And this is from that same dissertation. So you can see here, we have a contingency table. We're comparing two variables. These were about women who participated in WIC, and I have here somewhere WIC stands for the Special Supplemental Nutrition Program, SNAP, for Women, Infants, and Children program. So WIC program, it's basically like a social welfare program that helps very vulnerable women, get food and nutrition, right? Among other things, I think. Not an expert on that, but you either participated or you did not. It's binary. Now, food security, you're in two categories. You could imagine there's actually a continuum, but in her dissertation, she made it dichotomous. You were either in the food secure category or you're in the food insecure category. So if we're comparing food security and WIC, these are two binary variables. It gives us a 2x2 contingency table. We've got counts in there. This is real data, by the way. And you can see there's column percentages. So you can see that if you did not participate in WIC, you had a 17% chance of being rated food insecure. But if you participated in the social welfare program, you had a 32% chance of being food insecure. It sounds like there's a significant association there to me. So let's go conduct the chi-square test and see if it turns out that, yeah, these two factors are definitely correlated. They're related somehow. And so the chi-square test, we actually put here. So we put the chi-square statistic, we put the DF in parentheses. There's different notations you'll see floating around the world, including in these notes. I think this is the first time in the notes that we put the DF in parentheses. I'll say this is a pretty good way. This is probably the best way to report it. Chi-squared parentheses DF equals, the statistic was 4.65, and we have the p-value at 0.031. So this is this is APA formatting here. And you can see here the p-value is less than 0.05. Therefore, we conclude that we reject the null, and there is an association between participation in WIC and food security. Now, okay, that's a significance test, but what about our odds ratio? So the odds ratio has a really simple formula. So up here, it shows A, B, C, D. It labels the cells. By the way, this odds ratio is only for 2x2 tables. If you have a categorical factor with more than 2 categories, you cannot use the odds ratio. And so all we're doing is we're just applying that formula. A is 58, D is 55, B is 118, and C is 12. So you put that all together and you get 2.2. And I've actually put here a quote from her dissertation where she reports the odds ratio. The odds ratio is 2.22, meaning that the odds of participating in WIC are approximately twice as great for mothers who experience food insecurity as compared to mothers who are rated as food secure. Okay, so if you're like me, you're sitting here and saying, well, okay, the odds ratio is nice, 2.2, I can calculate it, but don't I just prefer to interpret this as like the percentage difference? Yes, I do prefer it that way. It's a little bit clearer to me. The odds ratio, though, it is an effect size, and as you continue studying statistics, you'll see effect sizes have many wonderful properties. And one of the most important is that I can compare an odds ratio of any 2 categorical factors across all the studies, right? I can actually also compare proportions because those are actually also standardized on a 0 to 100% scale. But odds ratios have better statistical properties, so they actually become more useful in quantitative analysis. But for just your baseline descriptive reporting, I do agree, I think you're going to agree with me at least, that the simple group proportion differences like that is a little easier to interpret. Okay, so we can calculate our odds ratio, and we see it's not terribly difficult to calculate, although I recognize it is difficult to interpret, and I've only given you one example of interpretation. But I will just say, especially if you're from the medical sciences or like a nursing program, you are going to be familiar with odds ratios. You will hear them. And I will leave it up to you as students to know whether you're in a discipline where you really need to focus on and master this interpretation of odds ratios. So I prefer the probability scale like most humans. There are some people who, for example, gamble. They actually only use the odds scale in gambling because you're paid out based on the odds. But most of us are not gamblers, so most of us will prefer the probability scale. Now, I've also put guidelines here. You know, if your odds ratio, and I'm just going to let you read this. Odds ratios are beyond the scope of the class. I'm not going to test you on them, but I do think it's a very important thing to be aware of. In the same way that Cohen's d complements a t-test, an odds ratio complements a chi-square test of independence. That's really the main thing I want you to remember. And, you know, when you get to where you have to report and interpret these things, I would say come back to these notes, do some Googling. I do that almost every time because, again, I just don't find, I can't remember these random rules. If the odds ratio is less than 1.68, it's a very small. 1.68 to 3.47, small. So, again, everyone has to look these up. You know, not easy to remember these things. Okay, so that's all for the odds ratio. And that's actually all for our lecture notes this week. Now, I do want to take a moment and I want to do 2 things. We are going to jump into, so if you click on the little description here, as I've done in the past, I put a little quick summary of what we're doing in the lecture. And then the optional SPSS material is going to be here in the bottom. So not in the modules, but here. And you can download this data set, chi-square data and chi-square output, and follow along with what I'm about to show you. You do not need to know SPSS to do the homework or be successful on the midterm. Sorry, the final. But I will tell you, it is really easy to do an SPSS, and it's really nice to be able to check your work like this. So it's worth learning if you're up for it. So with that said, let's dive into it. So I've already downloaded the data and I'm going to show you how to open it in a second. But I want to go back to our notes from last week where we learned about testing proportions. One of the things we learned is how to compare two population proportions. And if you think about it, doesn't that sound a lot like what we're actually doing? Last week we learned the large sample z-test. Now this week we're learning chi-square test. And yeah, we can actually, they're actually equivalent procedures. So what I'm going to do is I'm taking this example and I'm going to conduct a chi-square test on it. And in practice, pretty much 99 out of 100 times, you will see people prefer the chi-square test over the test for proportions. But I want to demonstrate their equivalent in these next few minutes. So what I've done, so how you open your data in SPSS is you navigate to it on your computer and you just double click it. And I already have it open. It's here. When you open that file, you're going to notice there are 934 people and there's 3 variables. There's ID, there's gender, and then there's support. So if you read the prompt, basically what we were interested in comparing here is between males and females. Did they support a single payer national system for healthcare? And we can see that 67.9% of women were in favor, while only 62% of males were in favor of such a system. The question is that difference in proportions, is that difference statistically significant? Now, if we can test that here with the z-test, and I can test it with the chi-square test, I think we all agree that I better get the same answer, right? You never want to be in a case where you can test it with 2 different procedures and you're testing essentially the same null and alternative hypothesis, but one gives you a different answer than the other. That is not what we want. And we will see we get the same answer. We get the same exact p-value no matter how we do this thing. So let's go ahead and do this in SPSS. So in SPSS, this is the data, and you can see again gender and support. And the first thing I'm going to do is I'm going to go to Analyze, Descriptive Statistics. And I'm going to be here in the crosstabs option. So again, Analyze, Descriptive Statistics, crosstabs. And because I've already done it, let me remove all this. So you can, it doesn't matter which one you put into rows and columns, you get the same answer. Before you need to put gender and support though, right? Those are the 2 variables we're comparing. And then click on the statistics box and ask for the chi-square. And right now, I'm not going to do anything in cells, but we'll come back to that in a second. So I'm going to hit OK. And the first thing I'm going to do is just check my data and make sure it looks right. So I have 489 females, 445 males. So I come back, we'll see 489 females, 445 males. We had 276 in favor for males and 332 for females, 276 in favor for males and 332 for. So you can see the data is the same, right? That's my crosstabs. That's my contingency table. These 2 by 2, 4 cells right here. And now the chi-square test, and you can see it's as easy as just clicking a few buttons. We have here a chi-square test, and how we would report this is I would report it like this: chi-square, I put degrees of freedom in the parentheses, equals 3.535, comma, p-value equals 0.060. And that p-value is above 0.05. So ultimately, it's not statistically significant. And I've given you a full interpretation of this here. A chi-square test of independence. So you can see chi-square reporting it here. Therefore, we conclude there's not a statistically significant association between gender. That should say support. So that's really it. It's almost a bit surprising when you start learning how easy it is to do things in software. So the hard thing to do in software is to know how to navigate the menus and get what you want, and also how to ignore. If you look at this, there's a whole bunch of stuff in this table. I don't need anything else. I'm looking for the Pearson chi-square. So I actually don't need these other things. These other things are useful if you like break an assumption or something, like the Fisher exact test is used when you have when you've broken assumption. Now, you'll also know on the chi-square, look, it's got a little A here. Look, it's telling me this. 0 cells, gives me a percentage, have expected counts less than 5. It even gives you the minimum expected count. Now, that's really good news because remember, the main assumption that we need to check on our chi-square is exactly that assumption. And you can, if you want the table of expected counts, you can actually ask for it. So let me go to descriptive, analyze descriptive statistics crosstabs. I'm going to ask for, where is it? I think it's in cells. Expected. So I just checkbox the expected one. And I'm also going to ask for column percentages, which we talk about in the notes. Then I hit OK. And you'll see my table's not as pretty because they're kind of jamming everything in there. But you can see you do have the expected. It's just the organization of SPSS is a little kind of confusing. But you also have the column percentages. So 48.2 plus 51.8 adds up to 100. 54.6 plus 45.4 add up to 100. So among those who support, 54.6% were women and 45.4% were men. Right, so those are column percentages. You can ask for row percentages, etc. And you also see our expected counts. So that's how you can kind of verify the assumptions. But SPSS will just tell you by default when you conduct the chi-square whether the assumption of that cell count less than 5 is met. So on the independence, that's going to be something you assess via the design. And then 2 categorical variables. You can't even enter the data into this procedure in SPSS if you don't have 2 categorical variables. It won't even give you the option. So, you know, those you just need to be thinking about, you know, making sure that you have satisfied those other assumptions. This is really the main assumption that you need to empirically, that is mathematically, check the less than 5 assumption. Okay. So that will be all for today. Please let me know if you have any questions on this chi-square stuff. And remember, the SPSS stuff is not in the main module. It's posted here as files that you can download. And I've also put my output. You don't technically need that. All you really need is the data set, and then you can follow along this video and execute the chi-square test as I showed you. All right. Thanks, guys. Have a good rest of your week.